Hello everyone. In today's class on advanced characterization techniques, we are going to try and learn something about extended X-ray absorption fine structure as well as surface extended X-ray absorption fine structure and near edge X-ray absorption fine structures. In the last couple of classes, we have been talking about diffraction as well as scattering of X-rays as well as electrons. But in today's class, we are going to focus on how we can use X-rays for getting spectroscopic information and therefore chemical information from the material or substance under consideration. So, as you can see over here, there are two different techniques, namely the extended X-ray absorption fine structures, the same technique with a different geometry known as surface extended X-ray absorption fine structure and near edge X-ray absorption fine structure, which are put together as X-ray absorption spectroscopy. So, in today's class, we will just get acquainted with these techniques. I would like to mention that both the techniques, namely the extended X-ray absorption fine structures as well as the near edge X-ray absorption fine structures, is based on similar principle. However, they differ in the regime of operation in terms of energy. More about it later. So, let us go back and see what exactly we have understood earlier in the course of our earlier lectures. So, all of us know, and which something that I emphasized, that extended X-ray absorption fine structures is essentially a spectroscopic technique and it gives us information about the chemical composition. However, unlike techniques like EDS, that is energy dispersive spectroscopy, EXAFS gives us information at the angstrom level about the chemical content or the chemical environment of a particular atom under consideration. It is based on the same X-ray absorption edge which we had touched upon in our second class while we were understanding the instrumentation involved in X-ray diffraction. So, just to recollect it again, here you can see a normal spectrum as a function of wavelength for say something like copper target. Herein you see how we get the absorption for a nickel filter, and here you see that the absorption essentially increases with the increase in wavelength. However, at a particular wavelength there is a sudden drop in the intensity and this occurs because of absorption. So, our today's technique EXAFS essentially focuses on this kind of a phenomena, this absorption edge that we are seeing in the figure discussed over here. So, we know that how does X-ray interact with matter? We had talked about elastic interaction which leads to diffraction. Now, the diffraction can be either wide angle X-ray scattering which we carry out on a routine basis in laboratories, or it can be according to small angle X-ray scattering which we had touched upon in the third and the fourth lecture. At the same time, inelastic scattering that leads to Compton scattering, which is studied using the X-ray Raman effect, was also touched upon in an earlier lecture by my colleague. However, what we are going to talk today about essentially is X-ray absorption. So, herein you can see that there is a decrease in intensity of the X-ray as it passes through a material. So, the extent to which this decrease in intensity occurs depends on the absorption coefficient mu, which essentially decides the extent to which intensity of energy beam is reduced as it passes through a material. The absorption edge that we had seen earlier is essentially a sharp discontinuity in absorption spectrum of X-ray when energy of photon correspond to energy of a shell of the atom. Now, we are going to talk about it in the next slide, but let me just put it mathematically, how absorption can be quantified. So, if the incident beam is of the intensity I0 passes through a material with thickness of x, the amount of attenuation that occurs is actually e to the power minus mu by x, where mu is the absorption coefficient, and therefore, the intensity after passing through the material gets modulated as I is equal to I0 e raised to minus mu by x. If we incorporate the density of the material, we can get I is equal to I0 e raised to minus mu by rho into rho x. This is particularly important when we are considering mixture of various material, and we can take the weighted average of the absorption coefficient as well as the density. Generally, it has been found out that the relationship between mu and rho is not only wavelength dependent, but also atomic number dependent. Now, on the right hand side, we can again see the similar curve of what we had seen earlier, where we have a critical energy Wk for ejection of k electrons from nickel, and this corresponds to a steep drop in the intensity and leads to absorption of the X-rays, of the copper X-rays, what we had seen in the earlier case. Having said that, what are the kinds of interactions that can occur when a particular photon of a particular wavelength is incident on a material? So, if a X-ray photon of energy h nu is incident and has sufficient energy, it can knock off an inertial electron. In order to do that, the energy of the X-ray photon has to be greater than the binding energy of the electron. Once this electron is knocked off from the inertial, it can go and become a part of the continuum. There are other possible scenarios that can also occur. Having said that, if the electron from the inertial is knocked off and goes to the continuum, we can get a transition from outer shell to the inner shell, and this transition is accompanied with a release of another photon which has a wavelength that is different from the incident photon. This phenomena is known as fluorescence, and we can also use the fluorescent photon to uniquely characterize the material under, or rather the element under consideration. Another possibility is that in case this inertial electron is knocked off, we can also have a release of another Auger electron from the outer shells in order to accommodate this phenomena. So, all this, including the fluorescent photon as well as the Auger electron or the photoelectron, will essentially characterize the element under consideration. If we can uniquely identify and correlate either the photoelectron, the Auger electron or the fluorescent photon with a particular element, we can get chemical information about the same. Now, this philosophy is used in a variety of spectroscopy technique and X-ray absorption spectroscopy, which comprises of extended X-ray absorption fine structures as well as near edge X-ray absorption fine structure, which is also known as XANES, is no exception. These techniques is comprise of modulation of X-ray absorption coefficients at or near the absorption edge. So, here again let us go back and have a look. So, this is where we have an absorption edge, and here you can see the wavelength. So, how and therefore, the frequencies also, and you can see that what all modulation occurs near the absorption edge is what is used as a fingerprint for the presence of a particular element using in these techniques. So, let us look how exactly the pattern looks like. So, if you recollect, this is how the absorption edge looks like. So, in this case, since it is energy, you see we are going this way, here is the absorption edge, and again it goes on increasing with decreasing energy. However, you notice if here the modulations which can be seen in this pattern. Here again I would like to point that the technique XANES, X-ray absorption near edge structures, are found very close to this particular absorption edge, while extended X-ray absorption fine structures, as the name suggests, is far away, therefore extended, right. So, all of them these modulations which are far off are essentially known as extended absorption fine edge structures. Now, to emphasize that whenever we talk about absorption edges, it has to be specific. So, if you want to study a particular element, you have to focus a particular edge. Now, this point is made clear in the spectrum shown over here. So, here again we see that indeed we are having two absorption edges, the L3 absorption edge of lead and the L3 absorption edge of bismuth. So, in the present scenario, we are focusing on the L3 absorption edge of lead. The region which is very near to this edge essentially comprises of Zane's spectra, while the region far away comprises of extended X-ray absorption fine structure. So, this transition or this differentiation between EXAFs and Zanes is a bit arbitrary, though there are ways of kind of quantifying it. As a thumb of rule, generally it is considered that at a wavelength of the or energy of the order of 100 electron volt from the absorption edge, Zanes is valid, while beyond say 50 to 100 electron volts, extended X-ray absorption fine structure are valid. So, as I had mentioned, EXAFs starts from 50 to 1000 electron volt from the absorption edge. I hope you appreciate that with increase in the energy, we see that there is the oscillations that we are getting essentially die out. Having said that, absorption of X-ray photon is actually accommodated by emission of photoelectron. Now, this photoelectron, unlike in the normal case, tends to behave like a wave, right? Like this is the basis of wave particle duality, wherein you see that our subatomic particles can also behave as wave. Having said that, the wave formed because of the photoelectron actually interacts with the neighboring atoms, and therefore they get scattered from there. Not only that, there is an interference between outgoing as well as back scattered photoelectron wave, and this leads to interference. Now, this is something that we had talked about time and again, right? Like we have the X-rays which are going, they meet in phase, there is constructive interference. If they meet out of phase, there is destructive interference. So, something very similar to it is happening. However, this is happening very locally and at the atomic level, and these modulations are essentially seen in the Zane's or for that matter EXAF spectra, and this essentially contributes to all the oscillations that we are seeing over here. So, all these oscillations that come, we will have a better figure later in the class, but the situation is very similar to what has been shown in the figure. So, here we see we have our essentially atom which is actually emitting electron waves. So, you see the electron waves are going. The moment they interact with another atom, what actually happens is they are back reflected, right? They are back scattered, and once these propagating and these back reflected, they interfere, right? They interfere, and depending on that we get, if there is constructive interference, high intensity, and if there is destructive interference, we get low intensity, and this leads to essentially the oscillations that we saw in the EXAF's spectrum. So, what kind of interaction that can take place? What I showed in the earlier figure is a very simplistic assumption, and here each and every atom is essentially just reflecting the waves in nice spherical form. However, this may not be true. There are various kinds of interaction that may occur. So, here we have some possible scattering or multiple scattering events have been figured out over here. So, here in the first case we see a single scattering path, right. So, like the electron wave is scattering from the red atom to say the green atom, and it is getting reflected from the green back to the red, right. While in this case we have a double scattering path which is shown over here, okay, and we get mostly for forward scattering angle of close to 180 degrees. Similarly, there is also quadrilateral triple scattering path and also triangular triple scattering path. I am not going to go in details, but I hope you appreciate that depending on the kind of interaction we are having, all the mode of oscillation is of the pattern is going to vary. Now, having said that, we can always find out what kind of interaction is going to occur between the two neighboring atoms and what do we expect to get as a output. More about it later, but remember that for a given atom, the kind of interaction that takes place depends on its neighborhood. Now, this is the very genesis of the X-ray absorption spectroscopy technique, wherein we can get really information about the atomic neighborhood of a particular atom or particular element under consideration. Because remember, in this case we are focusing only at the absorption edge of one particular element, like we can see over here. So, you focus on one particular element and you see the modulations for that particular element. So, we see that okay, if I have lead somewhere, what is the neighborhood of lead. Okay, so this is how it works out. Now, moving ahead, as I had mentioned, EXAFS gives information about the neighboring atoms. Not only that, it tells us what is the approximate atomic number, because remember, at the end of the day, the scattering tendency of the atoms is essentially dependent on their structure factor, and which you are quite aware varies as a function of the atomic number. Having said that, another important point that is very relevant is the distance between the two atoms. If you remember, whenever we talk about interference, what really matters is we are essentially going from the real space to reciprocal space. So, the same kind of thing happens over here, and depending on the distance, we are going to see whether we get constructive or destructive interference. So, all this information we do get using EXAFS. However, it is highly modulated. Having said that, one of the biggest advantage that we have with EXAFS is that it works very well for crystalline as well as amorphous materials, while our X-rays, particularly when we talk about diffraction, gives us very little information about amorphous material. At the same time, EXAFS can also be used for studying solids, gases, liquids and even gas. Having said that, one of the biggest advantage of EXAFS is in studying in situ processes that occur in different class of materials. However, EXAFS is not really as common as other spectroscopy technique, right, EDS, and the main reason for that is we need tunable X-rays to capture a particular edge. I hope you appreciate that whenever I showed the earlier images, we were going at a particular value of the absorption edge, and this means we need a source for X-ray which can give us energy over a particular range. And this, not only that, we also need a energy resolution which is very good, of the order of 10 power minus 4 volt in 1 volt, and therefore most likely and in most cases we have to use a synchrotron source for carrying out EXAFS study. Having said that, the main driving force for carrying out EXAFS is to study light elements like carbon, oxygen and nitrogen. Now, these elements cannot be very well studied using conventional spectroscopic technique. Having said that, we talked about different kind of interactions that occur, namely the electron, the free electron that is given out once a photon energy is absorbed. We also talked that there can be a fluorescent X-ray that can come off, and there can also be an Auger electron. So, all these signals can be used in EXAFS in one way or the other to get some information about the localized chemical composition. Having said that, EXAFS is generally used in transmission as well as fluorescent mode to get the relevant information. A general instrument wherein we can carry out EXAFS is shown over here, and you can see that we have a beam coming out from synchrotron. However, we need a double crystal monochromator to get a particular range of energy, and we need an incident flux monitor to see what is the intensity of the incident X-rays. Okay? Then it has to interact with our sample. If it is working in transmission mode, you can see that the synchrotron beam passes right through the sample, and we have a transmitted flux monitor which monitors the intensity after the X-rays have passed through the sample. At the same time, we also have a fluorescence detector to see what all kind of fluorescent photons or fluorescent X-ray that we are getting. So, having said that, I hope you appreciate that we can get information about the chemical environment in a particular material either using the fluorescence signal or the transmission signal. The point that is to be noted here is that in the transmitted signal, the frequency of the incident and the transmitted wave remains the same, while in fluorescence there is a change in the intensity of the not only there is change in the frequency of the incident photon. Having said that, for detecting the intensity of the X-rays, we essentially use ionization chambers. Other detectors like photodiodes, photomultipliers, as well as solid state energy dispersive detectors, as well as wavelength dispersive detectors, which we had touched upon earlier in this module, as well as I am sure it must have been covered in the earlier part of this course by my colleague, but most likely what we use in case of extended X-ray absorption fine structures are ionization chambers, as they provide high flux and wide energy range. Now that we have gone, so you see how simple, we have a very simple EXAFS technique, right? The instrumentation part has got nothing exotic. However, one of the most important criteria is the availability of synchrotron. Having said that, you see with such a simple instrumentation, there is a strong capability to carry out in situ experiments. So, we can vary temperature, pressure, doping, as well as orientation and concentration in a solution, and study how the chemical composition of the material under consideration is changing as a function of external stimuli. Another important thing that I have not mentioned yet is that there is ability for us to get the synchrotron and use a polarized property of X-ray. And if you have polarized wave of synchrotron or X-rays, we can get sufficient information about the orientation. This orientation, I mean like the kind of bonds that we are having between A and B. So, by EXAFS you can know that A is surrounded by B, but if you use polarized X-rays, we can not only know that A is surrounded by B or C, but also at what angle it is aligned with respect to A. This is particularly important for deciding the chemical bonding between the two species. So, as we had already discussed, EXAFS, what we do, we excite the core electron to higher unoccupied or continuum state. Now, for this we need an energy tunable source of X-ray photon to illuminate the sample. For instance, if I am having a compound, say A, B, C, D, and I want to study what is the neighborhood of say A and A or B, then I should be in a position to tune my energy to the absorption edge of A, B, C or D. Having said that, another important point is that what all we are getting, what all pattern we are getting, it is not just the absorption edge. As the name suggests, this is extended X-ray absorption fine structure. So, we should have the ability to provide photons with energy a few hundreds of electron volt below the absorption edge and up to few thousands of electron volt beyond the absorption edge. Okay. So, there is a strong energy dependence of the absorption spectrum, and we should be in a position to control the energy, and therefore, we have to use a synchrotron which gives us an energy resolution of 10⁻⁻⁴ volt in about 10 volt. So, as we can see, the EXAFS data is characterized by a step function centered at binding energy, broadened by measurement resolution lifetime of core hole and monotonically decreases with energy. Remember, what all we are getting is happening at the absorption edge. So, let us go back and just look at the absorption edge. So, if you go to the absorption edge, this is where you knock off an electron from the inner shell, and then there are these interaction between the electron wave, right, and this interaction leads to the oscillations that we are getting. So, in order to get that, there is a lot of superimposition of the signals, because there is not just one scattering event, there is easily a situation wherein you can get multiple scattering, and therefore, this makes analysis of the data slightly complicated. However, a very simple governing equation is given over here. So, here you see the chi of k is essentially summation n of j, which is nothing but the number of atoms which are surrounding a particular atom or element under consideration. The fjk exponential minus 2k square by sigma square is essentially the disorder term which actually decreases in intensity with the number of oscillations, and there is a electron inelastic scattering term. So, here you see we have a scattering term which essentially comes from elastic scattering, and here we have the inelastic scattering term which actually determines the interference, right. So, we have to see how much interference is occurring. Okay, so, this elastic electron inelastic scattering term is this one, the second exponential. The first exponential over here is actually the elastic scattering, right, like which dampens, and this interference term essentially decides what kind of an oscillation pattern that we are going to get. As you can see from this equation, the period of oscillations increases with the increase in frequency. Having said that, also there is an increase in the period of oscillation with increasing r, where r is the distance between the atoms under considerations, and also the intensity chi e actually increases as we have more and more j, assuming that, or more and more atoms, assuming that all of them are scattering in phase. Okay. So, now let us go and see how exactly EXAFS data looks like. So, you see here this is again our energy versus absorption coefficient, and you see the same thing, we do see that instead of getting a sharp drop, we do see a few modulations over here. This does not show a lot of information. However, once we convert it to chi k, k cube versus k, we see that there are lot of oscillations. I will tell you the reason why we are multiplying it with k cube, and I hope you appreciate that essentially it is done to actually see the oscillations at higher value of energy. As we move away from the energy from the absorption peak, we see that there is a lot of damping effect. So, in order to see the oscillations, if we plot chi of k versus k cube, we do see all the oscillations. Now, another important thing is this k is essentially in the reciprocal space. So, that is why you see over here we have the angstrom inverse, right. Now, this information can be taken back and plotted in the real space, and we do get this as a function of r, which is nothing but the distance, actual distance between the atoms under considerations, and this shows the intensity, right. So, this is what we are going to try and match when exactly we take the data. So, now I am going to show you some things about how exactly we do EXAFS data analysis. Having said that, I should mention that we use well developed software at different synchrotron sources, and one such software is IFFIT, which is used at University of Chicago. Now, these are available for free, and what you can do is you can take and try to analyze what all data we are getting from different synchrotron sources. So, you see over here, this is what we have, this is what the kind of data that we get, fine, which is nothing but mu of E versus the electron versus the energy, right. So, this mu of E comprises of both the things, right, for your Zane's data, which is very close to the absorption edge, right, which is shown over here and which we can separate, and the data which is far off from the absorption edge. But even before we do that, once we get a signal, the first and the foremost thing that we do is to subtract the background, and this is what has been shown over here. So, we subtract the pre-edge background and then we normalize it. We can also separate the Zanes, or a region which is very close. So, you see we have gone almost up to 100 electron volt and said that up to 100 electron volt I have Zanes, and beyond that I have X-ray absorption fine edge structures. We continue with that, and after doing all our pre-edge subtraction, we carry out post-edge subtraction, and here you see the kind of oscillations that we are getting, right, quite a few bit of oscillations. Now, what we do is we take the same part after subtracting the background and our chi of k versus the k, and you see this is the actual data that we get after doing entire background correction. As we had seen earlier, in order to see or in kind of modulate and see the oscillations, you can plot chi of k versus k square into k square versus k, and here you see how we get the modulated oscillations, and they are easily visible. Now, all these modulations correspond to a particular interference occurring between two atoms. Okay. So, now if you see, this is how it looks like. We had plotted chi of k versus k. Now, the same information can be taken back and plotted in real space. So, now you see we have chi of r versus r, and this r is in angstrom, and here you see we are seeing some characteristic peaks. Having said that, if you remember this chi of r that we are having as well as r itself, the Fourier transform of chi of r, it has a real part and an imaginary part. So, we have tried to match the real part, and we do indeed see that the red one shows that okay, there is a good match. Having said that, please note that there is the intensity is dying off at higher values of r, and once we plot k square versus chi of k versus k, you see that all the oscillations are visible, and we can see that there is a good match, though it is not visible over here. Having said that, once we get our chi of r versus r, we can go back in literature and actually find out what corresponds to which peak corresponds to what. So, this is just like JCPDS or ICDD, where we have a database. So, here we can see that this peak which we get between 1 and 1.5 angstrom essentially corresponds to FeO, while between 2 to 3 actually corresponds to Fe and Fe. So, by doing like this, we can see that we can fit in all different kind of peaks and get individual contribution from individual, for that matter here iron and iron oxide peaks, not only in real but also the reciprocal space. I hope with this analysis it is very clear that we can identify not only what all atoms are present in the neighborhood, but also at what distance they are present, and therefore, this technique gives us information about the chemical surrounding at the angstrom level. Here again I have just mentioned to you that we can carry out various tests in situ, like heating as well as applying pressure. So, just to show you what kind of effect we have, if we apply temperature, we see that there is a continuous decrease with increase in temperature. So, these are some practical limitations that we have, but remember the kind of oscillations, all these oscillations actually correspond to the interference between the waves that are being scattered from the surrounding atoms, and you see that as we increase the temperature, there is a decrease in the oscillations. Okay. Another important parameter, this chi of k, I hope you remember, like if you go back to the first curve, we see in this case we have mu of E, which is nothing but your distribution, and here I have swiftly shifted and I did not mention what exactly is chi of E, but let me just write that chi of E is nothing but mu of E minus mu. Okay, I have gone on the wrong side. There is no distance. Okay, let me just do it over here. So, let me say that this is my chi of E is equal to mu of E minus mu 0 of E. So, this is nothing but the differential term, okay, of mu 0. Okay. So, this is what we have done over here. Okay. So, having said that, what all we have talked about up till now is the basic, right, the basic physics for doing extended X-ray absorption fine structures. And I hope you appreciate that we are talking about very thin samples. Mostly I mentioned that we have a sample large enough so that the X-rays are able to pass through it. However, there are instances when we are looking at surface phenomena, and that is where grazing incidence is very important. And if we carry out the same X-ray absorption fine structures in grazing incidence mode, it is known as surface enhanced XAFs or SEXAFS. Now, the biggest advantage that we have is that we can irradiate a region extending from nanometer to millimeter range just by changing the angle of incidence. Having said that, we can also use the same concept of detecting either the reflectant beam or the fluorescence or even low energy electron, namely the Auger electrons, to get some information about the chemical environment of a particular element under consideration. As I had already mentioned, that the original equation of XAFs breaks down at lower k, where we have this near edge X-ray absorption fine structures. In this energy range, actually what happens is there are multiple scattering events and the dynamical calculations have to be incorporated. Now, these are too involved, and as such Zane's Zane's or near edge X-ray absorption fine structures is actually used only as a fingerprint technique, by which I mean that if you see a particular peaks in the Zane spectra, we can say that okay, this particular element is present. However, the quantitative analysis of this technique has not developed till date. However, the Zanes gives a lot of qualitative information about the coordination chemistry, molecular orbitals, band structure, as well as various multiple scattering events that can occur in a material. Having said that, I hope you appreciate that we can get excellent short range order information about chemical environment using X-ray absorption spectroscopy. We can also use this technique to study crystalline, amorphous materials as well as liquids. However, synchrotron radiation is almost always necessary for carrying out X-ray absorption spectroscopy. Another important disadvantage that we have is, though we know the chemical composition or the chemical surrounding, we have absolutely no idea about the oxidation states, and the theory that is involved for understanding EXAFs as well as Zanes is pretty complicated, and this complicates the use of this technique in getting some information with high fidelity. Thank you.